Welcome to Structural Analysis 2 video series unit number 3 flexibility method. Lecture outline: numerical problem on non-prismatic beam, part 2. This is the second part of a previous video. Our problem statement was analyze the beam shown in figure by flexibility method, and we have to draw a bending moment and shear force diagram. Now in the present case, non-prismatic beam is given. Now we was calculated the static indeterminacy, and we assign that static indeterminacy at C as vertical force Vc positive and moment which is anti-clockwise, and we calling it as mc, and sign is positive. So these are the our degree of static indeterminacy or redundant forces, and we call it as q1 and q2, and corresponding displacement in the original structure corresponding to this redundant. In case of Vc, there is no any sinking, there is no any spring force, so displacement will not be there. So dq1 is equal to 0. Also, due to the moment, there is no any sort of a rotation or rotational displacement in the direction of mc, so that dq2 is equal to 0. Then next is we were see our next step, which we was discussed in the previous video, that is a m1 diagram, and q1 and q2 is equal to 1. So these are the release structure with the q1 is equal to 1 and q2 is equal to 1, and m diagram with the redundant release the structure and keeping the load as it is. Then we saw this calculation of m considering release structure with the load. Then we calculate the moment for different zone CB, BD and DA, and for that we assign the origin C as origin for all zone, and according to that we put the limit, and also we have to consider the moment of inertia of each zone. After this, we gone through the M1 diagram, that means release structure with Q1 is equal to 1, and we calculated the moment due to that Q1 is equal to 1 by considering each zone, and also considering the that Q1 is equal to 1. According to that we calculate the moment, and that we were put in the column M1. Then we also saw the M2, that is M2 is nothing but the redundant force, and that release structure with Q2 is equal to 1. Okay, and again we consider the same zones, and then we calculate the moment due to that redundant force. Q2 is equal to 1. Now this is a part of a second video. Now move toward the displacement corresponding to redundant in a released structure that called as a DQL. So how to find out DQL? DQL is equal to integrating 0 to L capital M into small m divided by EI into dx. That means M column into M1 column, and also you have to add the zone CB plus BD plus DA zone, putting their limits. Now integrate M into M1. So now here, if in the first zone CB M is 0, so automatically M into M1 will be a 0. Also M into M1 for zone BD, that value will be come out 0. So only last zone will be there, and its limit is 3 to 4. So DQL1 is equal to 0 LM into M1 divided by EI into dx. So DQL1 is equal to 3 to 4, limit is 3 to 4, and the value is 300 minus 100 x into M1 is x into x divided by 2EI. Now moment of inertia is 2I into dx. So we have DQL1 is equal to minus 91.67 EI. Now next is DQL2, displacement corresponding to redundant in release structure. Now here, we have to take M into M2 column. Now again here, zone CB and zone BD, the M value are 0. So move toward directly DA for zone DA. So putting the value DQL2 is equal to integrating 300 minus 100x into 1 divided by 2EI into dx. Limit is 3 to 4. So by solving we have DQL2 is equal to minus 25 EI. Therefore DQL is equal to DQL1 and DQL2. Now putting the value, we have 1 upon EI in a bracket minus 91.67 and minus 25. So this is value of DQL, that is a displacement corresponding to the redundant in release structure. Now let's find out the flexibility coefficient. Now first is F11. So F11 means integration of M1 into M1 divided by EI into dx. Limits are 0 to L. Now let's put the value F11 is equal to first zone and limit is 0 to 2, and our value is M1 into M1, that means x into x divided by EI into dx, plus second zone, limit is 2 to 3, x into x divided by 2EI into dx. Third zone is DA and limit is 3 to 4 into M1 value is x into x divided by 2EI into dx. By solving this, we have F11 is equal to 12 divided by EI. Now second flexibility coefficient, F12 is equal to F21 is equal to M1 into M2 divided by EI into dx. Again integrating from 0 to L. So putting the value M1 into M2, limit for first zone, limit is 0 to 2. So 0 to 2 into x into 1 divided by EI into dx, plus second zone, the limit is 2 to 3 and value is x into 1 divided by 2EI into dx, and plus last zone, integration of x into 1 divided by 2ei into dx, and again the limit is 3 to 4. So by solving this, we have f12 is equal to f21 is equal to 5 upon ei. Now next coefficient f22 is equal to 0 to L, integrating from 0 to L into m2 into m2 divided by ei into dx. So now there are three zones, so add all these three zones and take their limits under the consideration. So first zone having a limit 0 to 2, so 0 to 2 into, now m2 is 1, so 1 into dx divided by ei, plus second zone limit is 2 to 3, and m2 into m2 means 1 into 1 divided by 2 ei into dx, and last zone is limit is 3 to 4, and m1 into m2 means m2 into m2 means 1 into 1 divided by 2 ei into dx. By simplifying, we have f22 is equal to 3 upon ei. So our flexibility matrix is 1 upon ei, putting the value 12, f11 is 12, f12 is 5, f21 is 5, and f22 is 3. Now next step is flexibility equation. So this is flexibility equation, dq is equal to dql plus flexibility matrix F into q. Now putting the value, dq is 0 and 0 is equal to 1 upon ei minus 91.67 and minus 25 plus 1 upon ei in bracket in a matrix 12, 5, 5 and 3 into q1 into q2. So by simplifying this flexibility equation, we have take this dql term toward the left hand side, so it become plus 91.67 and 25. Now our equation become 12q plus 5q2 is equal to 91.67, and second row is 5 into q1, 5 into q1 plus 3 into q2 is equal to 25. So this is second equation. By solving these two equations, we have vc and mc. vc is 13.64 kilonewton, mc is equal to minus 14.395 kilonewton meter. Now we know that redundant forces. Now let's consider the release structure and apply the known forces. Now redundant forces we know. Now let's find out the other unknowns. Now structure is determinant 1. So let use summation Fy. Upward is plus and downward is minus. So vertical forces, let's consider Va upward, Va plus Vc minus this vertical force downward minus 100 is equal to 0. So Va is equal to 100 minus 13.64. So Va become 86.36 kilonewton. 86.36 kilonewton. Now taking moment about A, so MA, let's consider anti-clockwise positive, MA minus this anti-clockwise positive, but by the value of this 14.39 kilonewton is minus. So put here minus 14.395 plus this 13.64 into 4, it will move in a anti-clockwise about A, so plus, that's why plus into 4 lever arm, and next is 100 kilonewton, it will move in a clockwise, that's why minus 100 into 1, the distance is 1 is equal to 0. So MA is equal to 59.83 kilonewton meter. Now find out MB. Now MB is nothing but D. The cross section changes at B. So let's find out moment at that section B. So the moment, let's consider right hand side. So plus this MC, that means value of MC is minus, so minus 14.395 into 2. So this rotate in anti-clockwise, so therefore the sign is positive, but the value come out minus, so put here minus 14.395. Don't consider this 2 because this is a directly moment. And next force is this vertical force 13.64. Now it will be rotate about this B point in a anti-clockwise sense. So plus 13.64 into 2. So MB is equal to 12.88 kilonewton. It come out 12.88 kilonewton. Okay. Now next point is, now we know the all moments. Now let draw the bending moment diagram. So this value is 12.88. So this is 12.88. Okay. So this is our given figure or given member. Now let first show the end moment at A. The end moment is 59.86 kilonewton meter. So positive means you have to keep your pen close to A and rotate in anti-clockwise sense. After one complete rotation, arrow come up, so show up. Now here at B, our value is 12.88 positive. So keep pen close to B and rotate in anti-clockwise sense about B. So coming down, so you have to show 12.88 downward direction. And last is at C, the value is minus 14.395 kilonewton meter. So keep pen close to C and rotate about C in a clockwise direction. So rotate in clockwise direction, arrow coming up after one complete revolution rotation, so show up 14.395. So this is your join with the line. So this is your end moment diagram. Now for point load, draw the free bending moment diagram. So that become WL by 4 is equal to 50. W is 100 into 2 divided by 4 is equal to 50 kilonewton meter. Okay. So portion which is not overlap, that you have to make hatch. So this is about your bending moment diagram. Okay. Thank you.